Hi, welcome to my presentation on my paper Efficient Bayesian Nonparametric Hazard Regression. My name is Matthias Kaeding. I'm a postdoc at the RWI Leibniz Institute for Economic Research at Essen. This paper is about hazard regression. Hazard regression is in general concerned with modeling survival times, where the classical example are survival times until death. But we can look at other events as well, of course. And existing approaches are flexible. They are often non-parametric, as is my paper. But the main disadvantages is that most existing approaches are computationally expensive, and they have a formulation which is hard to interpret for many practitioners. So my approach is to develop an efficient estimation framework based in a Bayesian, fully Bayesian framework, allowing efficient inference under general censorship. And this approach also allows easy interpretation of covariate effects in terms of survival time directly, which is easier than most existing approaches. For hazard regression, we often do not observe the exact survival times. Instead, we observe an interval for which we know that the true survival time lies in this interval. So the most common case is right censoring. Here we know that the true survival time exceeds a threshold. Another case is left censoring. And of course, the best case from an information perspective is no censoring where it observes the true survival time. And the main idea is to account for the censoring via the likelihood contributions. And the canonical, the benchmark model for hazard regression is Cox model. This is simply a model for the hazard rate. And the main component of the Cox model is unspecified baseline hazard. This is a log linear model for the hazard rate, which is simply the density conditional of an individual not having experienced the event. And in my paper, the perspective is shifted so that the idea is to not directly look at the effects on the hazard rate. Instead, we have another measure for covariate effect, which I will show later. But for the Cox model, it holds that one gets this expression for the survival function. The survival function simply gives the probability of being alive at a point in time. And this then depends on the integrated or cumulative baseline hazard, which is simply the integral of the baseline hazard. And the idea of my model is of my approach is to model the log of the integrated baseline hazard via monotonic P-splines. This nice switch up gives us a closed form expression for the likelihood simply due to the properties of P-splines. And we have a general linear predictor, which is extended with log-cumulative hazard rate, as well as other nonlinear effects, all modeled via P-splines. And like I said, the main advantage is that we get a closed form expression for the likelihood for all censoring schemes, making inference much easier and accelerating inference, because otherwise we would have to use numerical integration or another approximation. And the main idea of P-splines, which are used for the nonlinear effects, is that we have a simple weighted sum of B-splines, B-splines the B-spline function can be seen on the left side of the plot, and we then weight the B-splines and sum them up, and then get a function estimate, as can be seen on the right-hand side. And the main feature of B-splines is that they are very flexible, so we have to use some sort of penalization to counteract overfitting. And for this, there exists a random walk prior by Lang and Bretzka, which I apply here. And for F0, the log-cumulative baseline hazard, we have to get a monotonic function estimate. And a nice feature of P-splines is that this can be easily achieved by simply restricting the coefficient vector associated with a cumulative baseline hazard to also be monotonic. And this can be done in the modeling language I use, which is the popular language Stan, and I use a posterior simulation via Hamiltonian Monte Carlo in a fully Bayesian framework. So we then simply have to sample a monotonic vector for the log-cumulative baseline hazard. And the general advantages of this approach is that we have the sparsity of B-spline bases, so that all involved computations involve algorithms for sparse matrix multiplication, and this gives us advantages during the estimation stage and during the post-processing stage. And to the second stage then can be used to improve the interpretation of covariate effects using the general efficiency of the approach. For hazard regression, we have the situation that we cannot easily look at marginal effects in terms of the mean function, because this would involve extrapolation, which we generally don't want to do in a nonparametric framework. Instead, there has been an alternative measure developed called the restricted mean survival time. The idea is to have a measure which can be interpreted as the average survival time until the follow-up time sigma. So then we can interpret this directly in terms of an average survival time, which is more intuitive for many practitioners. And this has been done mostly for binary covariates. The classical applications is a treatment effect. And I extend this to metric covariates using partial dependent plots, as has been used in the machine learning literature. And the main idea is to average over all parameters and all covariates except the one I'm interested in. So you get a marginalized estimate of the restricted mean survival time, where we marginalize over all parameters and covariates. And this is done for grid of values. And this then involves numerical integration, because we have to integrate the survival function. And this again can exploit the fact that the P-spline basis is sparse, so everything can be quickly computed. And we also have closed form expressions available. A related concept which we can use as well is the average survival function, where again we average over all parameters and covariates instead of conditioning on the parameters taking values such as 0. And this shows the partial dependence plots for the applications from the paper. The application looks at survival times of advertisement on MLB Scout 24, which is a homepage where people can offer apartments for rent. So we are looking at the survival times of advertisement until they expire. So the general idea is that advertisement expire more quickly for nicer flats than for less nicer flats. And the partial dependent plots on the right-hand side are the partial dependent plots for the metric covariates, where we have the extension in the paper. And the most interesting variable, I think, is the rent. So we can estimate a nonlinear effect of rent on the restricted mean survival time. And actually, the estimate looks pretty linear. And this can be interpreted as a direct effect of rent on the restricted mean survival time. So the interpretation here would be that higher rents are associated with higher survival times, so that advertisement where the rent is too high are not are longer on the homepage. For model choice, we use the expected log predictive density criterion. This is a measure for the generalizability of a model to unknown data, that is for data which we haven't actually seen. This can be estimated using leave one out cross-validation. This, of course, would be very slow if we would do it directly, but there exists an efficient estimator which we use, where one does not actually have to perform the leave one out cross-validation. And this again directly uses the likelihood as computed from the model. And here again, we have again the general advantage that we have a closed form expression for the likelihood. And the plot here shows the estimate of the criterion, how it behaves if we input several covariates. And we can see that we have a very high jump for the nonlinear function of the number of missing elements, for example. That is for the elements where the person who put the advertisement on the homepage did not write in the information. Yeah, I also have done a Monte Carlo simulation of the modeling strategy, where we look at how the mean squared error behaves under varying censoring schemes. And in general, one can say that the mean squared error is highest under a high fraction of right-censored observation, and of course lowest when there's no censoring at all, which makes sense as there's no information loss if we have all information about the survival times, of course. And it's also pretty low for interval censoring. But this, of course, in general depends on the width of the interval, where larger interval, of course, means a larger amount of information loss. And in general, one can say that the estimation strategy works as desired if we have a sample which is large enough. So we can say that it does not work very well for small sample sizes, which generally makes sense because we have a very complex model here. So overall, one can say that Monte Carlo simulation tells us that the model works well. And on this nice note, I close my presentation and thank you for the attention. And yeah, I'm happy to answer all your questions during the live session.